reaction quotient and small equilibrium constant. Let's have a look first at this component whenever we have a small equilibrium constant, and then we'll deal with our reaction quotient near the end of this video. As you can see, the previous video for this one, we had to create a nice table when we had our values here, and using C is equal to N over V, we had to create an ICE table using concentrations. So we have I, C, E, and we're going to be putting our reactants and products. So we have our H2 here first, then we have our O2, and then we have our H2O. And let's bring it down. Now for our initial concentrations, remember we have to do a disclaimer that this is all going to be in moles per liter. We have to put our concentrations. Well, like I said, N is going to be our 0.18 for hydrogen gas. Our liters is going to be in volume over there. So just going to be the same value, just be 0.18 divided by 1 liter. So you just get 0.18 moles per liter. Again, this is all in moles per liter, so I'll just put 0.18 over here. And for O2 is the same thing, right? 0.23 divided by 1, so you just get 0.23. For H2O, it's not formed yet initially, so we're just going to be putting a 0. Now we're going to be putting our changes, so it's always going to be x as a variable to determine whether it's been increased or decreased for change. And of course we have 2 moles of it, so obviously we have to put a negative, right? Because negative means it is being consumed, we're losing it so that it's making the product. And of course there's a coefficient of 2, so let's put 2 moles over there. And then we're doing the same thing for O2, or x here, but there's only 1 coefficient, and of course it is being consumed, so we'll be putting a negative over there. For our H2, again, it is being produced, we are gaining it, so we have to be putting a positive symbol there, coefficient of 2, and then there's an x. We're just going to add them all up for equilibrium, so get 0.18 minus 2x. Doing the same thing for this one. Do the same thing for this one, add them all up. Alright, now let's put them all as an expression, because with an expression we'll be able to figure out the equilibrium concentration of just water vapor. Okay, not just all the reactants and products, we're only looking for water vapor, so we still have to use a expression. So let's put just K, okay, because this is our temporary equilibrium constant. And then we have to look at our products over the reactants. Okay, so we got our product here, so it's H2O, and of course it should be squared. It is gaseous. And then we're doing the same thing for our oxygen and our hydrogens. So H2 here, it is also squared, it is gaseous, multiplied by our O2, not squared, it's just to the power of 1, and then this is also gaseous. Now what do we have in the question? The question does say that we have a KQ value of 1 times 10 to the negative 7. Again, this is KEQ. This is a permanent, okay, not a temporary equilibrium constant. We always start off with a temporary equilibrium constant. Can I change this K into the KEQ? Yes, because this is a gas, gas, gas. We're not dealing with any solids or liquids. See the link in the description about these constants, whether they're pure or not, so that we can determine K to become KEQ. Again, that is a prerequisite video before watching this one. So we have K. It can easily become KQ, so let's change that over here. So we're just gonna move it up here so that we can actually substitute our values correctly. So our KQ can now go into here. We have 1 times 10 to the negative 7. There we have it. And then we're just gonna implement our number of numerical values into our H2O. Our H2O here, what is it? It is 2x. So we're just gonna be putting our 2x within that. And then we're going to do the same thing for our H2. What is our H2? Well, we have 0.18 minus 2x. Of course, this has to be squared. And we're doing the same thing for our O2, 0.23 minus x. There we have it. Now, if we look at our KEQ, it is an extremely small value. If it's an extremely small value like that, we can actually use a rule. An approximation can actually be made. If this KQ is at least 1,000 times smaller or lesser than the initial concentrations of either reactant. So if we get this value over here, our 1 times 10 to the negative 7, multiply it by 1,000, you obviously get 1 times 10 to the negative 4. This value here is still much smaller than either reactant's concentration. Let's look here. We have our H2R 0.18. Obviously, this is much smaller than 0.18. Same thing. Let's compare this with our O2 reactants, 0.23 concentration. Of course, this is still much smaller than 0.23. So this rule now applies, which means that our equilibrium over here can actually be simplified, because right now it's kind of a gruesome, annoying process to use the quadratic formula, because these are not the same. We can't make them a perfect square. Okay, in the previous video we looked at perfect squares. Look at that video link in the description if you need to. Okay, prior to this video, this is not a perfect square, so we got to use a elongated process of quadratic formula. But if this is going to be very, very small using this 1,000 rule, we could actually simplify this so that this 0.18 could just be 0.18. We don't need this change as we've indicated here within the expression. Same thing here. We don't need this change as indicated in the expression. So we can actually just simplify this. So we just get 1 times 10 to the negative 7. We got to keep what we have up here. But for our reactants, we simplify it so that we just get 0.18, just our concentration. And we do the same thing here, 0.23. Now it's so much easier, so much more simple. Do not forget to keep your squares here and your other exponent there as well. So now all we need to do is continue to bring it down. So we get 2 to the 2 gives you 4x squared, obviously. Continue it, so we get 0.18 squared multiplied by 0.23. That's it. Obviously this is technically over 1, because if there's nothing on the bottom, we just assume that there's 1. Now with these fractions, we can now cross multiply easily, so you just get 4x squared times 1 just gives you 4x squared, and then you just do this, this, all multiplied, so you just get 1 times 10 to the negative 7 times 0.18 squared, that gives you 0.0324, and multiplied by our 0.23. Let's bring this all the way up here. So we get 4x squared is equal to what? You get 7.452 times 10 to the negative 10. Now divide by 4, so we isolate for our x. So you end up getting 1.863 times 10 to the negative 10. Square root this side so that you can square root that side. X is equal to 1.36 times 10 to the negative 5. There we have it. Now we're going to get our concentration for H2O. What would it be? You just got to get our 2 multiplied by whatever x value is. This is our x value. Multiply by 2, you end up getting 2.73 times 10 to the negative 5. And of course, all of this is in moles per liter. This is your answer. Now let's look at our reaction quotient. Our reaction quotient is also known as QEQ. What is this QEQ? Well, this QEQ has the same formula. As our KEQ, our equilibrium constant, the one that we were just describing over here. But it may not be at equilibrium. So, what is the point of this? Well, we use this to see if there will be a shift in the reaction. So I'll just put Rx in for reaction to see if the shift in the reaction prior to equilibrium will move to the left or to the right. So whether it's going to go towards a reactant or the product side. Also, a small little note here that I want you to always remember. For our KEQ, so I'll just put if our KEQ that we end up getting, and I'll show you how to do that in the practice problem after this. If the KEQ is ending up greater than our KEQ, then the more products are present compared to the reactants. Okay, this means that the product must convert to the reactants for equilibrium to be met. If our KEQ is going to be less than our KEQ, this means that more reactants are present. And this is obviously compared to the products. And if that's the case, this means that there are more reactants than the products, so this reactant over here must convert into the products. It must become products in order for equilibrium to be met. And of course, this last note here, KEQ being equal to our KEQ, I'm pretty sure you can kind of tell what this one would be. It is at equilibrium. Let's illustrate this in a practice problem. We have our reactants, we have our products, and we've been given our KEQ. So I'll write our KEQ over here as 142.3. They've given us these values here. I also want to add in this question, is this at equilibrium? Is this at equilibrium? And if it's not, what direction is it going to go? Like, where is it going to shift? For the reaction to favor it, right? For the reaction to be favored. Okay, we have our values over here. We know that we have to use our QEQ, our reaction quotient here, within our expression. And we know that our reaction quotient has the same formula as our KEQ. Remember, our KEQ formula is always going to be the products on the top and then our reactant concentrations on the bottom. So for our QEQ, we can do the same thing. So for our QEQ, we can put our concentrations on the top. So what is our concentrations? For our products, we have PNH2. So where is that? That's this one over here, 5.74. And then we can do the same thing for our HCl, 2.04. And then we can do our reactants here, our PCl3. Our PCl3 here is 2.15. And then for NH3 here, it is 1.21. Now remember, we have to look at our coefficients. If there's a 3 over there, we got to be putting that as the exponent. This HCl has a 3 as well, so our HCl was our 2.04, so I have to be putting it up here as well. Okay, the other ones just have one coefficient, so we don't really have to worry about it. Okay, there's just a 1 here and a 1 here. So all you need to do is punch it in your calculator, what value you're going to be getting. So I end up getting 12.79. Now we compare this QEQ value with our KEQ. Obviously this here is much smaller, so we're just going to be putting our QEQ is smaller than our KEQ. What does this mean? This means that our reactants are heavily present. So if there is greater reactants, where do you think it's going to shift? Is it going to shift to the left or is it going to shift to the right? Well, if there are more reactants, then remember with Le Chatelier's principle, if there is an increase of reactants, how are we going to alleviate this stress, the stressor? Well, we obviously have to go and achieve equilibrium, so we have to shift it towards the product. So that will be towards the right, okay? So it will shift towards product formation. See my previous video for Le Chatelier's principle. The link is in the description if you need clarification on it. Pretty similar. Remember Kp, same as Kq, but using partial pressures instead of molar concentration. So our Kp, they give it to us as 2.11. We're going to use our Qp, which is the same thing as QEQ. Again, just using partial pressures instead. And all we need to do is be putting our products on the top over our reactants. Okay, so what is our product going to be on the very, very top? We have PCl3. So I'll just write that out. PCl3. Of course, the 4, and as well for our reactants we have P4. Okay, we are not going to be putting our P4 because it is a solid, so then we're just going to be looking at our Cl2 instead, and it has to be to the power of 6. Again, both of these are gaseous, so now we can continue to go on forward. Our Qp is going to be our PCl3 concentration, which would be 3.04. This is going to be to the 4 all over our PCl2, which is going to be our 1.21, and that's going to be to the 6, right? Can't forget that one. All you're going to do is now do your little calculation. What do you end up getting? You end up getting 27.21. Look at this value versus our Kp. As we can see, our Qp is much greater than our 2.11. What does this mean? This means that our products are favored. Okay, sorry, our products are more heavily present. So, therefore, if we have greater amount of products, using Le Chatelier's principle, in order to alleviate that stress, what's going to happen is going to shift toward the reactants. That's the answer. I want you to try this question on your own. Obviously, this is going to be our green question of the day. Try this yourself. Please pause the video, and I'll be giving you the answer shortly. This is the answer.